Hello everyone. Today we are going to see the topic of principal components and curves and surfaces from 4th unit unsupervised learning. So this is the syllabus of unsupervised learning. From the syllabus we are going to see about principal component and curves and surfaces. Let's dive into the topic. When we use PCA is nothing but principal component analysis. It is one of the type comes under feature extraction. So, before entering into the topic, first of all we should know some basic definitions to understand the topic deeper. What is dimension and its types? What is feature? What is variable? So, dimension is nothing but a position, size, characteristic or feature to describe something of the thing. Type 1 dimension, 2 dimension and 3 dimension. So coming on to the definitions of feature. Feature is characteristic of the data which we use to analyze. Each feature represents one aspect of the data to make it understand easily and to predict easily the outcome. So variable is similar to the feature as it represents specific type of data. Each of the data holds some different values from each of the observations. So both the feature and variable are used to describe the characteristic of the data set. When we use PCA, when the higher dimensional data occurs or when the higher features we have, so we will apply this PCA. So as the number of features or dimensions in the data set increases, the amount of data required to obtain a statistical significant result increases exponentially. This can lead to issues of overfitting, increased computation time, reduced accuracy of machine learning model. This is known as curse of dimensionality. So due to the issues of overfitting, increased computation time, reduced accuracy of machine learning model, it is also known as a curse of dimensionality. And I hope everyone knows overfitting. We have already seen in the previous chapters. So to avoid these kind of drawback, we are using this principal component analysis. Additionally, some machine learning algorithm can be sensitive to the number of dimensions, require more data to achieve the same level of accuracy. To get an accurate result, some machine learning algorithms are sensitive. So we use this principal components to avoid these drawbacks. To reduce the dimensionality and to extract the feature technique that aims to reduce the number of input features while retaining as much of the original information as possible. Principal component analysis technique was introduced by the mathematician Carl Pearson in 1901. It works on the condition that while the data in higher dimensional space is mapped to the data in a lower dimensional space, the variance of the data in the lower dimensional space. So it will map the higher dimensional space to the lower dimensional space. It will reduce the dimensionality, it will reduce the feature from the original data set. Principal component analysis is a statistical procedure that uses an orthogonal transformation to convert the set of correlated variables to the uncorrelated variables. PCA is most widely used tool in exploratory data analysis and in machine learning for predictive models. So the main goal of principal component analysis is an unsupervised learning algorithm technique used to examine the interrelations among the set of variables. So it will relate the relations between the variables and it will give the result. The main goal of principal component analysis is to reduce the dimensionality of a dataset while preserving the most important pattern and relationship. So it will reduce the dimensionality, it will reduce the feature from the original dataset and it will give the important patterns and relationship between the variables without any prior knowledge of the target variables. So principal component analysis is used to reduce the dimensionality of a dataset by finding a new set of variables smaller than original set of variables. From the original set of variables, it will be reduced and it will be the smaller than the size. So there is a step-by-step explanation of principal component analysis. So let's see the step 1, standardization. First we need to standardize our dataset to ensure that each variable has a mean of 0 and standard deviation of 1. Z is equal to x minus mu divided by standard deviation. So mu is the mean of independent feature and sigma is the standard deviation of independent feature. Coming on to the step 2, covariance matrix computation. Covariance measures the strength of joint variability between two or more variables, indicating how much they change in relation to each other. To find the covariance, we can use this formula. Covariance x1, x2, summation I is equal to 1 to n x1I minus x1 bar, x2I minus x2 bar divided by n minus 1. So if the value is positive, means as x1 increases and also x2 get increases. If the value will get negative, means as the x1 increases, the x2 also decreases. If we get the 0, means there is no direct relationship between the variables or the datasets. So coming on to the step 3, compute eigenvalues and eigenvectors of covariance matrix to identify the principal component. So let A be the square n into n matrix and x be a non-zero vector for which Ax is equal to lambda x. For some scalar values lambda, then lambda is known as the eigenvalue of matrix A and x is known as the eigenvector of matrix A for the corresponding eigenvalue. So here the non-zero vector means at least one of the element is not zero in the matrix. So here the lambda is known as the eigenvalue of matrix A and the x is known as the eigenvector of the matrix A. So eigenvalue is used to predict the most important data, most important pattern from the dataset, and the eigenvector is used to predict the most relationship between the datasets. So after predicting these eigenvalues and eigenvector, we will get the principal component and we will sort the principal component in the descending order to get the higher priority information datasets. After then, we will transform the data according to the formula of total variance divided by explained variance of component into explained variance ratio. So this is the example for principal component analysis. So here we have a three-dimensional cylinder diagram. So let's see this image. So this three-dimensional image is converted into two-dimensional as a circle. Then the two-dimensional is converted to the one-dimensional as a straight line. So it is also the one of the another example for principal component analysis. So taking a data set of a student to get a academic performance, either a mark or grade. So we need a data for first higher priority data set. So here we have three options. So how much time they spend to study, and prior marks or grades, and how many friends they have. So I think the first image will be the higher priority because how much time he or she spent to study is a necessary data for this problem statement, and we will need the third image as a higher priority because the prior marks and grade will also be used to predict the particular student academic performance, and we will take the friends example for the lower priority. So this is the principal component analysis. I hope you understand. So let's dive into the topic of curves and surfaces. Curves is a line represent relationship and boundaries between data point in one-dimensional or two-dimensional spaces. Surface relationship between 3D data points. So when you have one or two-dimensional data, you can represent pattern using curves. For example, if you are trying to cluster data in a 2D space, the decision boundary which separates cluster might look like a curve. For surfaces, in higher dimensional data, patterns are represented by a surface. A surface is a generalization of a curve, but in multiple dimensions. For example, when clustering in 3D data, clusters may be separated by surfaces. So in simple, we can say one or two dimensional data can be drawn like a curve, and higher dimensional data like 3D dimensions or more than 3D dimensions can be represented by using these surfaces. So here is the difference between curves and surfaces. Maybe it can be asked in 7 mark or 13 mark. So first one is the definition. We have already seen about what is curve and surfaces. So I repeat once. Curve is a line that represents relationship or boundaries between data points in one-dimensional or two-dimensional spaces, and a surface is the multi-dimensional generalization of a curve representing relationship or boundaries in 3D or higher dimensional spaces. Dimensionality usually applies to lower dimensional spaces 1D or 2D, applies to higher dimensional spaces 3D and above. For the use case typically used when visualizing and clustering 2D data or finding relationship in simple datasets. So we will use for the simple dataset, not for the big datasets. So here in the surfaces we will use for the higher dimensional datasets, not for simple datasets. So coming on to the visualization, can be easily visualized in 2D as a line or boundary separating clusters. Can be visualized as a plane in 3D, but beyond 3D, visualizing surfaces become abstract and challenging. So comparing to the curve, so in surfaces it is quite challenging. So here they use a k-means algorithm where clusters may be separated or curves decision boundaries in 2D spaces. And for the surfaces they use principal component analysis, which we have seen now. So which can find complex surfaces separating clusters in higher dimensional data. So the computational complexity is easier in the curve, and for surfaces it is more expensive and harder to interpret the dimensionality due to the more number of features. So the interpretation is simple in the curve and it can be understood easily because of low dimensional spaces. For the surface it's quite challenging because of multiple dimensions. We can't able to predict easily. And we have a real world example, clustering customer preferences in 2D spaces, and for the surfaces dimensionality reduction in higher dimensional data, compressing image data or gene expression data into 2 or 3 dimensions. So this is an image how the curve is mapping for when we use for 1 dimensional and 2 dimensional. So it look like this, and for surfaces it might be look like this. So just look onto the image. So the dataset will be mapped as a surfaces according to the Chern's predictions and Chern's predicted variables. So yeah, here I have given a reference link. You can refer further about these topics. I have attached the Java T-Pine and Geeks for Geeks link.